let's go to our Q&A session. And again, I
Okay.
should mention to everybody, I should be upfront that some aspects of this are proprietary, right? You're going to be pursuing a patent. So, but other than that, again, anybody, if you want to, let me see, how do we raise our hands? Option Y on Mac or Alt Y on Windows to raise your hand. And you can also type those questions into chat. And actually, let me see, Harold has one.
What about Ubuntu or Linux?
Oh, you know what? Those would probably follow the Windows. I would bet you. Yeah, because they use a Windows keyboard. So it'd be Alt Y. So let me go to Paul LaViolette first. Sir? Oh, Paul, you're still muted. Here, let me ask you to unmute. Sorry.
Oh, you mentioned about cooling the copper down to 5 above absolute. Have you considered 40 Kelvin? Because you can get that behind a sun shield, as long as you're out in space. That's one question.
Can you only get 40 Kelvin? I was considering a CubeSat as a test for this, but if you can only get 40 Kelvin, I think that only brings you down to 100 times more, or even just 10 times more. Actually, it's a parabolic thing, so it probably only gets you 10 times more.
The other thing I'd like to mention, like in your slide number 5, where you were showing the triangle with the current flowing, and you were saying that's Lorentz. I would like to suggest that that's ampere forces that are involved. In fact, your equation is very much like the ampere force law.
Well, I'm taking that straight from the Wikipedia page on the Lorentz force. And this is I know there's this debate about the ampere force and the...
I've dealt with Wikipedia and I don't always believe them. You know, it's the standard physics view. They're still stuck on Lorentz law, and there's a lot of these phenomena that can be explained by ampere law. It's also I squared.
Whatever it is, but I think they give both essentially the same prediction as regards force. And what the tests have shown, certainly the high current tests have shown it incontrovertibly, because you have very narrow ranges there of the amperage in the coil, and you have a very limited time window to impart that. I've even done calculations, because the people at Hilo assured me that the sample box was purely plastic, because they're used to having metal test systems, and they don't want heavy metal interfering with that. So it's a purely, the whole thing was in a rack. The surge current generator was much lower than the sample box, and the sample box was several levels above the rack, above the generator, to keep that isolated from the sample. And the sample was in that purely but even if it had been, in the worst case, that it had been metal, I estimated that even though the current in the coil gave an incredible 3 Tesla in that electromagnet, it would decay rapidly in the 10 centimeters to the 7 centimeters to the wall. That decays extraordinarily rapidly to 0.04 of a Tesla, and that cannot produce the 8,000 newtons which would be necessary to explain the motion of that coil.
What I'm saying is the ampere force can explain with your V diagram. The force you were getting can be explained that way. Also, you mentioned the railgun. Have you considered the pi frame experiment by Panos Pappas? He basically disproved that it was due to Lorentz force, and it's due to ampere force. Well, and also the Nasikas experiment that I was involved. I was doing the experiment.
You were involved in Nasikas. Well, he was using the wrong direction of his windings.
What do you mean by wrong direction? He had a
Because
conical coil.
he had the conical coil, which the windings going
Around.
around and not around the coil, as it were, not spiraling upwards, but in fact going longitudinally, so they were all equal in length. But if
Well,
we had,
I think from our experiment, we disproved that it was due to the Lorentz force, because that initially he was assuming that the Lorentz force would propel it along the narrowing direction.
his calculations were wrong, that the field would not have been impinging on the wires in the right way to cause a force. It would have been much better. My simulations all showed, based on Maxwell's equations and integrating whatever force in the system over the system, that such a coil, incidentally, amusing that both Scheuer and Nassikas used a frustrum, a truncated cone. But in the case of Scheuer, it was pumping microwaves through it and getting micronewtons of force, which Timar seems to have shown now is purely due to heating of the system. And in the case of Nassikas, I would say that it was one of those that my simulation showed wouldn't work. And with the superconducting coil, you would have expected huge amperage. What sort of amperage did you have in there?
80. And we
80.
did it gradually. We went up gradually.
Yeah, of course. Yeah, that's the thing with
because of the limitation you mentioned about exceeding the point where the superconductivity fails,
Yeah, it will fail due to quench. That's why
yeah.
in most of these superconductors, that's the other point I wanted to mention, that if you want to start, you turn the coil in your the key in your electric car, and you expect it to start, and it takes hours to start superconducting coil. Sorry, loading.
It was just an experiment to see if it would show some thrust, and it was a zero thrust.
Yeah. And
maybe we could continue this by email, or I'd be interested to hear your opinions on the Seekus coil.
Yeah, I could send you an email on that about the details.
ethericgate@gmail.
Yeah.
Okay.
Well, Paul, thank you, sir. Okay, so let me go to, Harold Tavares, actually. Harold, let me see if Harold is, okay, and Harold, okay, we missed him, his connection was unstable. He had asked if this Lorentz system has any resemblance to the PNN thruster, and that was something that we covered back on July 31st. Hugh, are you familiar with the PNN thruster at all?
I'm not sure. What was it again?
You know what? Let me see if Jeremiah Pop is here. Jeremiah, let me ask him, or Jeremy Reese. Oh, there's Jeremiah.
Yeah, I can answer that question. PNN works on according to them, Lorentz force between the two elements of the antenna structure. It does not rely on any geomagnetic fields whatsoever. So it's a self-contained system, works within an enclosure, and works in any orientation. They did test it in every orientation and rotated it. The force is equivalent, and it also builds over time. So
is this the one which Cameron Jeffries developed with the?
Give me a second, I'll show you which one.
Oh, if that's okay.
It is a cone, an antenna-like structure. Okay.
Yeah, I think Jeremiah.
Yeah, it's this one here. So.
And it's two antennae. And
right.
It's essentially,
you can change the angle between these effectively, and then they saturate. So there is a force that's going down one side, up the other. The fields are not taking place in the near field closest to these elements. It's compressed, so they have to travel through space that time delay that they take creates a phase interaction, creating, especially in this region here, a spatial compression where you end up with the force basically pushing on this thing. So, and
Yes.
Perez's
Yeah.
drive is different. Perez's drive is also a V-shaped drive, which people will probably ask about and compare it to. And that is a pulling engine, meaning that it'll try to pull itself upwards like this instead of push out like the rocket like this one does.
Yes,
So,
because the two currents are going in the same direction, then the force is upwards.
yeah, and the difference with Perez's drive is that if you look at it from the side, you know, this is a straight element in this case, and this is just as a demonstrator to show the simplest possible design still functions fundamentally based on the fact that fields travel at a finite velocity. But with Perez, he uses effectively loop antennas. They are fractal loop antennas, but they're still a current loop. And so you're talking about the magnetic component instead of the electric component, whereas this is mainly the electric component. This is the you know, the charge flowing through and the differential velocities between when those charges are flowing that you're getting the greatest force. So.
Right. Well, I did consider antennae like that as well, but the only problem with them is that you can't get as easily a sort of a coil antenna. You can't get multiple units within that. The beauty of a coil is you get multiple units in there. For example, even in that high current test I had 20 turns in the coil. And so n squared was 400. So that boosted the amperage in the coil, which was already 10,000 or 14,000. It was multiplied by 20, giving 28,000 or something amp turns in the coil, and so that really gave a huge force.
It is pretty wild to push off that field, and it's interesting though that instantaneous force that you can get seems so much larger than what would feasibly be there. One would intuitively think, you know, the geomagnetic field is not intuitively strong, but yet it actually is incredibly strong depending on how, you know, much you can push with it.
It is incredibly strong, which is why it messes up all those low current experiments. With that surge current pulse, the beauty of it was, even though you're only putting in a few watts, you're putting that in 20 microseconds. So that means you're operating at 60 megawatts over that 20 microseconds to give those few watts. And they go in there, they don't even heat the coil extraordinarily, only about 6 degrees or so. And it simply shoots up, gains that velocity. So you could actually use that in some way. You could use that for propulsion. Certainly on a satellite, you could use that with a surge current pulsing, say, once every millisecond, microseconds once every 20 milliseconds. That would easily.
Yeah, I'm kind of already surprised that we don't see a lot more, you know, geomagnetic response systems for satellite steering. It seems like a really easy and simple approach, but we don't really hear hardly anything about it. Yet there's that massive field that's just unutilized, and we have satellites dropping out, running out of propellant, really. I mean,
yeah, exactly. And some tests have been done with tethers going down, getting the Earth's field to interact with the tethers.
Oh yeah, we've seen the space tether snap, just burned itself out, too much current. So there is definitely a lot to utilize there. There's no doubt about that.
Exactly, because they're very thin wires, so it doesn't take much amperage to actually burn them out. But it is great that they were actually burnt out. It shows how efficient they were.
Well, and it also shows how much more current was there than what was expected or anticipated. And that's definitely worthwhile looking into.
That was a bit like in my high current test. From the surge current generator, they were describing, oh, your impedance is too high there in that coil. You won't get maximum amps in there. But I would have been satisfied with 10,000, but the fact that we got 14,000 amps was magnificent.
Yeah, that's not bad at all. We built an impulse generator that fires about 9,000 joules of energy, and it's got just a massive stack of parallel cap banks for individual or 4 banks of 8 parallel capacitors each, just to get that initiate current. And so we tap them at the center and have very short arc bars. The total loop path is about maybe, I want to say, 1.5 feet max. So it's a pretty short distance between the caps and the work go to electrodes that suffer. And we've seen some interesting effects, upwards of 1.5 mega amps at direct short is what it'll do. But it's blowing stuff clean apart and liquefied wires in ways that I still can't explain.
Right.
And they
Wow.
weren't hot. It didn't liquefy them in a way that they were hot. It's like it stripped the electrons out to such a degree. They were going so fast when the wire broke. All that extra charge just ripped the electrons out. The covalent bonds like fell apart, and this thing became jelly-like and just snaked its way through.
It
And
was like a microcoil, although it wasn't destroyed. It retained its shape, but all the wires were pushed apart.
but it wasn't because of heat. It's like this
No, it's just
deformation
the-
effect can actually take
the
place in
repulsion-
more than just
The
Lorentz
repulsion
forces.
between the wires, because they all have the same current in them, and they all are pushed apart. Really, you need more mechanical constraints, even for these surge current tests, not only for the superconducting tests, but you need really constraints on there to deal
Yeah,
with
a
it.
cylindrical solenoid experiencing high impulse current will try to flatten itself into a disk and expand outwards as well. So it's really hard to constrain it into that enclosure where it won't blow the sides clean off and just try to fatten out. So I've seen what they'll do, and they can be quite violent. I've seen many thousands of pounds tear bolts right off, no problem.
Yep.
Yeah. Well, if it's okay, Jeremiah, thank you so much.
Yeah, that's
sir.
all. I didn't have anything else to add.
Oh,
I
no,
was-
no, that's okay. It was a wonderful conversation. That's why I didn't want to interrupt you guys. But yeah, if it's okay, let me go to Michael Boyd next. Michael?
Hi, Hugh. Nice talk. So I'm curious if you, so I have, I had a job once where I worked on a small linear accelerator that they used for oncology for treating brain tumors. And they would create a 6 million volt X-ray with this linear accelerator. And the power source was this thing called a magnetron.
Oh, yes. Yeah.
I'm curious if you ever considered using that kind of where
Yes, I consider a magnetron, because a magnetron has the beauty of sending a huge current through a very thick electrode. And I thought of having a sort of a V-shaped electrode where you could get a huge force out there, but again, it needs funding for all these things. And also in terms of accelerators, they've been a great source of inspiration to me. For example, in the LHC, they have such huge electromagnets that you can work out, in their documents, they actually quote 10 to the 5 newtons per square centimeter per on the electromagnet. So they really have to have massive mechanical constraints in there to stop those coils exploding apart. Because this Deasy-Lorentz pressure.
magnets, do you know? How many Tesla the magnets are that you're talking about?
Oh, I think in the inner thing they produce at least 5 Tesla.
Wow.
Remote from the surface, so it must be more Tesla on the surface. It must be tens of Tesla.
Wow. Okay, thank you for answering my questions.
You're welcome.
Well, and Michael, thank you as well, sir. And let me see, we had another hand up and then it disappeared. And let me see. Sorry about that. Oh, you know what? I think maybe that individual dropped off the conference. Well, so again, guys, if you want to raise your hand in Zoom, and I should probably write this down someplace that's easier. It's Option Y on Mac or Alt Y on Windows. Ah, there's Paul. Paul, you had your hand up. Go for it, sir. Oh, Paul, you're muted again, sir.
Okay.
There we go.
All right. What was previously said by the fellow about his wire fragmenting, that sounds a lot like ampere forces. I just wanted to, that's all I wanted to say.
Oh, okay.
I think ampere forces are something neglected because physics tends to teach about Lorentz forces. They don't say too much about ampere forces. I think they're an important thing to take into account.
Right, I'll look into that a bit, but so far the Lorentz force has served me fairly well.
Yeah. Well, so let me ask. Let me see who else has questions for Hugh. And I think if we're almost out of questions, let me see if Franc Milburn is with us because Frank is not here. So what I think that we're running low on questions. I think part of that is this time of the day. I know it's evening for you, right? And so
Yes.
yeah,
Midnight.
it's that mid. Oh, okay. Well. Okay. Oh, William, go ahead, sir.
Can you hear me there?
Yeah.
My remark was just about cryogenics. That's something I have some prior exposure to. If you were trying to just build a small satellite, you could use conductive cooling and a pulse tube to do that. Those are relatively small. It's not CubeSat, but it's smaller than a 50-gallon drum. So it's something within the scope of maybe a grant proposal. It'd probably be a big one, but that's something very possible. And it would help you to avoid the transporting of cryogenic fluids. You could cool this thing down in space.
That's great. Yeah. That's what I always wanted, a sort of a shield behind which the absolute cooling of space could come into effect. And what sort of temperature can they get down to?
Ooh, good question. The fluid is helium, I believe, in the pulse tube. So you're going to get down to, I don't know, 10K, I think something in that order of magnitude.
Good.
Just off the top of my head, it might be a little lower.
Yeah. Let me see. And Jeremiah had mentioned in chat, he'd mentioned, let me see, the key to use of cold copper is electron drift velocity. He'd mentioned graphene and then nanofilament bismuth also as possible materials.
Yes, I was looking into bismuth, but for a system involving possible faster than light travel.
Ah, okay. I see another conference session appearing before my very eyes.
That would be another talk on itself, but
yeah. Well, you know, actually, let me go to Will really quick, and then we are ahead of schedule a little bit, so I'm going to have Frank come on. Frank said about 5 minutes, and he'll be on there. Will, would you like to go, sir?
Yes, on the cryogenic question, various types of military binoculars use cryogenics. They use micro Stirling engines. So that's another area you could look into. That's all.
Okay. And they're probably using pure copper rather than superconducting.
I believe that they're using YBCO.
Oh, so it is superconducting.
Yes. And also Japan just released a new either 8 or 9N copper wire a few days ago. One of my
So
staff had pointed out to me from the Japanese news.
that would be very efficient, because then you could get down to more than 1,000 times more, the less resistance with copper. You could get down to maybe 100 times less resistance. 10,000 times less.
Hmm. Okay, well, and again, anyone else with questions? Oh, Michael,
So
sir?
why is that you can get so much lower resistance by improving the purity of the copper? What atomically happening to make that?
It's because the resistance in copper is due to the impurities in it mainly. If you imagine the actual copper lattice, it's like a metal lattice, and the electron carriers are moving smoothly through it. And every now and then they hit an impurity and they say, I don't like that, and they heat up.
Well, I would understand the scattering effect due to the impurities.
Yeah, scattering as well, and
It would would
vibration.
there be an intrinsic impurity in the copper wire?
I don't think so. In the purer you get, the more smooth the lattice, and therefore the smoother ride for every electron.
Yeah, that would make sense.
Thank you.
Thank you, Michael. Let me, and actually there is Frank right there. So let me do this. Let me go to Will, and then we'll wrap things up after Will's question, and then we will go to Franc Milburn.
Can you hear me? Okay.
Yeah.
Okay. Yeah, I just wanted to answer Michael Boyd's question as a material scientist. So, Michael,
Hello.
essentially what's
Oh.
happening is that the amount of oxygen in the copper has been reduced so much that it allows a better conductivity. And this is this is really the biggest problem now in copper is how much lower can you get the oxygen molecules? And that's what 8 and 9N is all about.
Oh, so it's oxygen is acting as the impurity then.
Yes, that's correct. Yes.
Okay, thank you for clarifying that. It's appreciated.
Yeah, thanks.
Wonderful, wonderful. Okay, well, so we actually have Frank with us. So let me do this. I want to put this on gallery view, and I'm going to mute everybody out here real quick. And everyone, please give a giant applause for Dr. Hugh Deasy. Sir, a wonderful presentation. Thank you yet again. And so what I'd like to do now is